Well, welcome back. Please welcome Maciek. He is a software engineer with 2 decades of experience in Java, Scala, and Rust. He has worked on projects of all sizes, and he created Nussknacker, if I pronounce that correctly. In this talk, he will explore how different programming languages can work together through FFI, scripting, WebAssembly, and what really happens under the hood when they do. So please welcome him.
Okay. Well, hello. So it's great to be back again at HipCon. My first time was like 10 years ago, and that was a really long time ago. And if you remember, that was called Vox Belgrade. But some things did not change, and I'm really happy to be here. Like, for example, Dejan also doesn't change for the 10 years, so this is also great. And yeah, for those last 10 years, I've been working in different companies. Again, unlike Dejan. and a long time ago when I started, I was working at Tok, a very nice software consultancy in Warsaw. Then I moved to InsurTech, to Hyper Exponential. And then, yeah, I did some crazy things there. And right now I'm with MapTiler, who's kind of like a small company doing digital maps, but the beautiful ones, not like the Google ones. So go try it out if you want. And with all those companies, I've been working with very different programming languages, as was already mentioned, right? So I spent almost my whole life with Java, Scala, and JVM stuff. But then I've moved to Rust, Python, or NodeJS, right? And sometimes they were in different companies, different services, but sometimes everything was mangled together, right? And the question is, okay, so how do they actually can communicate? How do they work together? And sometimes it's pretty easy, right? Sometimes it's pretty easy, and fortunately in my current job, I also have the easy ways available, where I have just a Java service. It produces a bunch of gigantic JSON files, not related to security, don't worry. And another service is just consuming that, right? So this is the best you can get, right? You have batch interface, no worries. Everything is just like, it just works. But of course, usually you need something better, either for latency, performance, or whatever reasons, right? So for some people, natural way would be to start with any kind of like microservices connecting with gRPC, HTTP, and so on. And for many cases, this is fine, right? But sometimes you need something better, right? Because such approach introduces a lot of complexity. You start with one call, and then another one, and then another 5, and you end up with the service mesh, API, gateway. And if your service is meant to be used by your customers, right, who just want single Debian or single CLI tool just to be installed, then offering them a whole Kubernetes solution probably is not the way to go, right? So we need something better. And what can be better than intra-process communication, right? You just have single process, single binary, and then everything works together, right? So why we want to do this? Firstly, because of architecture simplicity, especially when you want to deliver some single package to your customers. Also because of performance, right? Because no matter how fast your HTTP is, or gRPC, or whatever, or Kafka, right? There's still latency. There are still 2 processes, usually 2 computers, and so on. And of course, some more performance is also very much welcome, right? But we'll start with something very simple, which maybe not super related to what people are usually doing. But let's think about the case then when you have a service, right? And you just want to make it pluggable, right? So your customers will give you a pieces of business logic, some general rules, and you want them to integrate into your service. For example, just to compute some calculations, to do some summing, or to perform some validation or custom rules, right? And usually you want to have something simple that they don't mess around with, that just won't break your code and so on, and to be able to provide even some code completion tools like we did with Nussknacker quite a long time ago, right? So what you really need is kind of like expression language. And the interesting case is that there are quite a few interesting ones. One of them is common expression language developed by Google to facilitate writing custom rules for security, for various permission checks, and so on, right? So there you can put your own custom functions, your own custom records. You can do the filtering. So there is basic Lambda functionality. So it's pretty cool in that regard, or mapping. So it's like very simple, but it can give you quite a lot of possibilities. And what is particularly nice is that it also has it's also pretty safe and fast, right? So you cannot screw your system too much with the users providing those expressions. And if you want something more complex, right? Because expressions sometimes are just not enough. Then what you can do is actually to embed, well, whole JavaScript, right? Because what language can be simpler than one in your application? And of course, there are many ways to do it. For example, Java has a long and bumpy road of integrating various scripting engines. But what I wanted to mention is something called QuickJS, which is a very small JavaScript engine that's kind of like easily embeddable in, for example, Rust or different languages. And then you can just use it in your program, right? You just pass some JavaScript expression or part of the program. You set some global variables, and yeah, it just works. Of course, this is not fully fledged JavaScript. You won't be able to call window API or make any kind of like system calls or access files. And this is good, right? Because you don't want your customers to do that, right? You just want some custom logic to be performed. But for many cases, this is simple enough. This is simple enough. The common expression language is also a good thing. Embedded JavaScript is much more powerful, but still quite simple. This QuickJS thing is really convenient to use. For example, you don't need the whole. It's pretty small binary. You don't need the whole ecosystem. Like for example, in Rust you have Dino and so on. So this one is smaller. And what we covered is that okay, we have one language, and we want to invoke. We have our system, and we want to invoke some pluggable components, right? So we want to invoke some kind of like simple, maybe high-level language, just to be able to make our system more configurable, more programmable, I would say. But what if we want to do something else? Something, I would say, the other way around, right? So we have a system developed in this kind of like high-level language, friendly for our developers like JavaScript, TypeScript, Python, and so on. And we want to invoke kind of like this not so friendly lower level languages like Rust, C, and so on. Well, of course, the first question is, why would we want to do this, right? And the first thing is speed. The next thing is to be able to use plethora of existing old, for example, scientific libraries for C, C++, Rust, or God forbid, Fortran, right? Because some of the scientific code is still based on Fortran that my father wrote like 40 years ago. And the next reason is, of course, speed once more. And these approaches were very successful, for example, for the Python, right? Where in Python you have a plethora of very interesting, very successful extension libraries that are written in C or Rust. The most well-known is, of course, NumPy and Pandas, which kind of like, I think, are the real reasons why the Python is the language of the data science. In some sense, also, you can think about PySpark as an example of that. And then you have newer Rust-based one like Polar's, Data Fusion. These are kind of like, I would say, modern versions of NumPy and Pandas written in Rust and kind of like more flexible. So how is it really possible? Well, the reason is that the Python itself is, well, written not only in Python, but in C, right? And if you have C code, you can use the ancient methods of calling different libraries, dynamic linking, using shared libraries, and so on, right? So somewhere under the hood, your modern data scientific Python code just using the ossified technologies from like 50 years ago, just to be able to call different C libraries. And Python is in some sense special, maybe not so special, but it's good in that regard because it also provides a very rich kind of like C API for those extensions libraries to interact with, well, with the Python world, right? With Python objects, with Python, I don't know, you can see exceptions, stacks, and so on. And this API is pretty well known, documented, and it's kind of like stable, right? There are, of course, different Python versions and so on, but still you can use it. And if you have a C API like this, then of course you can have Rust bindings. Of course, those Rust bindings are, well, not so pleasant to use, right? Of course, they are highly unsafe. You have to deal with the pointers and so on and so forth. So nobody in their good mind would try to use it directly. I mean, some people would, but but these are the real weird quirks. And we need something kind of like that is a little bit more high level than that. And here comes one of the most interesting libraries or platforms for Rust, and this is Pio3, which provides Rust bindings for Python, including tools to create these native extensions. And the slogan is like, writing native extensions has never been easier, and I can testify that, yeah, this is actually true, and Pio3 is pretty nice and interesting library. And how it works, of course, you need to configure some stuff in your Rust toolchain, which is not so difficult, not so important. And then when you build your, for example, library, what you get is kind of like, of course, you need to deal with architectures. We'll get to that in a moment. What you get is kind of like normal, I would say, SO file, right? This is the Linux binary containing the library. And then the toolchain will embed all of that into the wheel file, which is kind of like normal Python package, which is, of course, glorified zip file, but let's not talk too much about it, right? So you configure it, you run it, and at the end, you just get kind of like standard Python wheel. And let's look under the hood to the code, how it looks like in Rust. So here we say, with some annotations, right, that, okay, I want to expose this function to Python, right? It just sums the numbers, adds something, and whatever. Simple Rust function. And then after the toolchain processes all of that, you can just import it as kind of like normal Python code, invoke it, and voila, it will work, right? So this is the simple case. Of course, this is too simple to be kind of like useful, but you can also expose to much more complex structures. For example, you can expose real classes with real methods with your own custom constructors and so on, right? And then again, you import it in Python, you use it, create the values, and it kind of like just works, right? So this is a simple, easy way, right? So you declare the class, you declare the methods, right? And voila, in Python it just works, right? Of course, you need some custom annotations for the constructors for different things, but in general, this is how it is. And the great thing is that you can also abstract away the thing that you want to expose to Python and hide your normal Rust code somewhere in different crate, in different package or module, right? And then, so here we have this internal structure that is kind of like your normal Rust code. And then just wrap it in some Pio3 wrapper that's suitable to be used by Python. And then again, you're just using that, and the internal details are kind of like not exposed to Python, but they are just usable by this data exposed binding. And this is just standard Rust code. You can do whatever you want there. And the interesting thing that you can also use the things in different directions. So here you can see we have kind of like normal standard Python code, class declaration. It does something, whatever it is. And here we want to actually use this Python code from Rust. And we also can do it thanks to the C bindings. So here we expose the account function. And here we get let's not talk about the gory details of those bound and by any. It's manageable. It's not that complex, and you can just call the methods on Python objects. You can extract certain Rust values via some, well, more or less implicit conversions, and just again do some logic with it and return the result, right? So here it's the other way around, right? We call Python from Rust, and this is also perfectly fine. This is also perfectly possible with the PyO3 and C bindings. Of course, there is also performance penalty because calling Python is, it involves reflection, dynamics, and so on. But in some cases, this is the way to go. So these were the simple cases. We can expose classes, methods, functions. There are kind of like a lot of built-in conversions of common types like numbers, certain types of strings, or even containers like lists and so on. And it's possible to invoke Python API from Rust. But then there is yet another question, and that question is, okay, what about long-living objects? If we want to mix Python and Rust go in kind of like more stateful way, right? Because we know that Python is kind of like this high-level garbage collected language, right? Whereas Rust has its own memory management, all those lifetimes, ownership rules, and so on. And turns out it's also possible, but then, of course, the abstractions are leaking a little bit, and you need to be careful. Let's see what will happen if we want to have interface more or less like this, right? Basically, some Rust-based cache where this is how we want to use it from Python, right? So we create some cached instance, and you have a lambda that will provide you with, with the cache value, right? And then you just get the values. And of course, we start with something, with some structure that will be exposed as Python class. There will be the getter function, and there will be this cached object that will be present or not, right? So this is why it's option. And here you can see that what we're storing in this Rust structure is something called py of py any. And py any is kind of like normal Python object that's represented. And this py is a wrapper that's essentially telling the Rust and PyO3 that, hey, this is the Python object. I'm storing it in Rust. So you need to, well, more or less deal with the problem of reference counting, of garbage collecting it, who will free the memory, and so on and so forth, right? So still, this is visible, but it's not so difficult to use in most of the circumstances, right? But there is some mechanisms and some logic to make it work correctly. And when we want to actually use this damn thing, this is again, this is one more way of exposing stuff from the Rust to Python. We annotate stuff with getter, and for Python it looks more or less like a field, right? Of course, it's not like a real field like in Python, but yeah, this is how it works. And what we are seeing here, when we are getting those values of these cached objects, you can see there is this invocation of clone ref here, clone ref there. And this is what I meant, that we need to deal with this kind of like transforming our values from this automatic memory management of Rust to the garbage collected realm of Python, right? So again, we need to tell the machinery that, yeah, we're returning that, we're storing it, and somewhere under the hood, the PyO3 is taking care about reference counting, interacting with Python, garbage collection, and so on. So it is still usable, workable, but sometimes you need to be pretty careful not to screw things up and not to leak memory and so on, right? In more difficult cases, it's not so easy, but still it's possible, right? So here is the slogan that, okay, most of the things can be exposed pretty easily, right? But sometimes we cannot escape this change of paradigm, right? And we have, when a language with kind of like garbage collected memory management and language which has kind of like different memory management need to work with each other somehow. Somehow the things need to be, in some sense, reconciled. But this is still manageable. And one thing that is, I think, not so widely known as the Python C API and PyO3 is also that the Node has similar Node API, right? Also available in C, and there you can also do extension packages, extension modules in Node. The API is kind of like, I would say, more modern than Python because, of course, Node is a bit more modern language. So, for example, there are some built-in things that enable you to do async programming, unlike Python, where you have to. Well, it's not so easy. And also in Rust, we have quite a few libraries. One of them is an API RS that do the similar thing to PyO3. That is to expose this Node API to Rust and to be able to expose Rust code to Node. This is something that we quite heavily use in MapTailor. And then we won't get into all the details because we don't have that much time. But in general, this is how it is, right? Again, you put some annotation, and then somewhere in the node, you just import it from this or that extension module. Of course, this is kind of like simplified code, so don't put that much attention. And yeah, it kind of like just works. And also, you can also expose things like classes, methods, and so on. So it works pretty in quite similar way. And of course, there is this problem that you need to know which architecture to invoke, but there are certain helper scripts that will just guide the code to pick the correct library. Because here is the difficult and problematic bit of this whole foreign function interface using the C APIs, and that is the portability, right? Because we have our nice Rust code, and what we want to provide to the users is plethora of different binary files for different architectures, right? This is like Win32 for whatever reason. There's Darwin for Mac, and there are different flavors for Linux, right? Either Musl or libc, and there are many of them, and sometimes it's quite difficult and messy to understand what we actually need to provide. Of course, from the kind of like Rust compiler's perspective, it's not that bad, because somewhere in the between there is kind of like intermediate binary version that is LLVM, so it's kind of like low-level virtual machine, but it's like nothing like that. Anyway, there's an interesting bunch of tool chains and tools that make compilation easier for different architecture, but still the problem remains, right? Because somewhere under the hood, we use this new shiny NodeJS, Python, Rust, and whatever, right? But under the hood, all those binaries are just containing the ancient, for example, ELF files with some headers that contain keys pointing to the operating systems that no longer exist for like 40 years. If you go to the description and see how the format is actually structured, you can see that, okay, so this is like 40, 50 years ago, and it's like, but we still need to live with it, right? Because C is somewhere underneath still the kind of like blessed language. And here's the problem. For example, this is the animated GIF that I've made for how many actual files there are in PyPy for downloading pandas, right? And you can see that, I don't know if it's like 30, 40 or whatever, and there are different wheel files for different Python versions, which is kind of like understandable, right? Because Python changes, but also for many architectures, like both RAM, the Darwin versions, and also, surprisingly, also for different libc versions, which for people who don't know how stuff works under the hood might be pretty misleading. For Rust stuff, like for example, polars, sometimes it's a bit easier, right? So I don't need animated GIF here, right? Everything fits on the screen, but still you can see that this is somewhat weird, right? That okay, I have tool built with Rust. I want to use it in Python, and here, still in the in the version specifier, I need to specify, okay, what libc, glibc I'm using, or if I'm using Musla and so on. So the gory C problems appear. So the portability is, well, again, it's solvable, but sometimes it's much more difficult than it seems. I remember when I was compiling pandas for some ancient Python versions, and yeah, that was not a good experience. And there's yet another kind of like, I don't know if it's bigger, but still significant problems with using such extensions, and that is kind of like no sandboxing, right? We are just using, well, the shared library like in C, right? So they don't scream, but you know, we have some address space, no really security features. We need to trust the library that I'm including. Yeah. I see this spirit in her heart, right? And there are also some different problems also related to how those extensions model works under the hood. For example, pretty limited loading or unloading capabilities in the runtime, right? This is stuff that also, well, that also bit me quite hard in one of our projects when we wanted to, well, dynamically load and unload different pandas versions, and turned out not to be really possible because, again, this is a difficult problem, and the way how C extensions works are not so optimized to our modern world, right? And sometimes there is some runtime cost we also need to think about. Usually it's not that high, but especially when you invoke functions the other way around, so from Rust you call Python, then you need to remember that, right? But still using Rust or C or C++ to implement performance critical parts when we have a nice abstracted, separated API is the way to go. And this is used by quite a few companies, I think both well-known like Figma, Dropbox, Signal, but also, well, by great companies that might be not so well-known, like my previous employer, HX, or by us in MapTiler. So this is fine. This is, in many cases, this is the way to go. And there are also interesting projects popping up from that. For example, some time ago I read about UniFFI. This is a project for Mozilla, and it provides, again, some framework or toolchain to generate multi-language bindings for us to different languages. So you write Rust code once, and then it just generates bindings and libraries to use in Python, Go, Swift, Kotlin, and whatever, right? So it's kind of like a bit more simplistic than how Py3 works, because you normally don't want to call the language the other way around. But still, I think it's quite nice way to do it. But if we use this approach, we still need to remember that under the hood there is C. There is this 40-year-old or 50-year-old or God knows how much old legacy that is just sitting between our newer languages. And it precludes this approach for quite a few things, like, for example, for using in the web, right? Where in the web they also wanted to optimize critical paths. They wanted a small size of the binary. They wanted portability. But in the web you also need security, right? Because just using any shared library from a web browser probably won't do. So here is, from this problem, another approach popped up, and this is the WASM, right? This is the WebAssembly. And again, this is a bit different approach because WebAssembly is an assembly for conceptual machine, right? So this is, and the idea that we will provide a different assembly language. It won't be based on this old ELF or SOF files, but, well, it will be quite low level. There is a text format, but usually you don't want to mess with it. You don't want to read it. This is more or less how it looks like. It looks almost like Lisp with all of the parentheses, but it's not fun. This is more of an assembly language. And again, you do have some, in this assembly language, you do have some exports, you do have some functions, and you interact with the memory. You have, in a way, pointers and so on, but to some kind of like simplified linear memory where you can interact with that, right? And the promise of the assembly language would be that it's so versatile that it's the last plugin technology we ever need. And of course, 2025 is the year when the WASM becomes the right runtime, not just a browser hack, right? So the hopes are high for quite a few years. And why is that? Well, because this is how it started, right? The idea was to have this WASM deployed to the browser, right? And the code would be written in various languages like Rust, C, or Java, because why not? But then people realized that, hey, if we can do this, then maybe, we can also do that, right? So we won't run this WASM only in the browser, but also in different runtimes written in Rust, Python, Node, and so on, right? So we will have, instead of the C stuff sitting in between, we will have WASM and everything will be great. And this is employed, for example, by Cloudflare workers, where you can write the code in Rust, compile it to WebAssembly, deploy it to Cloudflare, and then it will work just seamlessly based on this technology. And again, you can write some Rust code, put it into the through the toolchain and the tools that will generate the assembly, and it will again just work. Another interesting case is, for example, SQLite, which is written in C, was also compiled to WebAssembly. You can invoke it, for example, this way from Java, and it's like, there's a single file, 800 kilobytes, so you can say that if you can do it for SQLite, then you can do it for whatever, right? And this is, in some sense, true, but still there are some problems, like how do you access Time API? How do you open files? How do you, for example, invoke HTTP? Or even how do you use strings, right? For the browser, you don't need most of the things because you don't need to mess with the syscalls. But yeah, for example, this is how you use kind of like vanilla WASM, how you interact with strings, right? This is kind of like pretty low-level stuff. You get the bytes, pointers, length, and so on. So it's like, it's not so pleasant. And of course, you need some tooling to get around with it. And if you need such tooling, what else can you do than make a committee? There's the Bytecode Alliance and more specifications. So there is a specification called WebAssembly System Interface, and it should provide us with the clocks, random systems, and various API to interact with the outside world of the WASM. And also even more exciting thing, that is the component API, which tells how different WASM modules will communicate with each other using some, again, interfaces to make stuff work. So all of that is very nice, but unfortunately, it's still not ready. And because it's kind of like designed by committee, then, it takes some time to make everyone agree upon it to make things working. So some people say that it will never happen. Some say it will happen, but just not yet. So I think this is a space to closely look at, right? But some of the things are still in kind of like a flurry, and it's not so easy to understand how to actually do non-trivial things, right? But I think the foundation model is quite good. There's lots of movement going around. The tooling is getting better and better. So it might be the future, but who knows? And we need to finish. So yeah, I think the slogan is that combining different language paradigms in a single process is possible, sometimes is fun. And for example, in one of my previous jobs, what we did was we started with client Python code invoked inside giant monolithic Python application, which was problematic for many reasons. And what we ended up is having one Python invoking Rust code, which itself invokes Python code from the customer, which has another Rust SDK, which invokes Rust SDK from different things. So that was kind of like really, really, well, interesting, especially because these were two very different Pythons, but you can do, yeah, very, very complex and interesting things with this approach. And if you want something simple, safe, and reasonably fast, then maybe let's try first with the expression languages in the embedded JS. Then you need low-level performance, syscalls, and agree with portability issues. You can go with FFI, with Rust C. And if you are not afraid of complexity, you want flexibility and complete platform, then, well, try to consider WASM and VASI, but you know, I think it's still not its prime time yet. And we also need to remember that challenges remain: different idioms, portability, non-friendly language barriers. These are the barriers to do it easily and safely. And I think this is all. Thank you very much for listening. I hope you'll enjoy the rest of the conference. And the last thing, did you know that Inuits have 16 words for snow? You did. If you didn't, go ask Miriam downstairs. She told me to put this slide on, so yeah. That's not from me, that's for her. But yeah, go downstairs and ask her, and thank you very much. And yeah, see you.